So in this problem, we're requested to find the magnetic field at a point O, which is the center of an arc AC, and the magnetic field is going to be due to the wire, which is shown here. It is made of three sections, A prime A, AC, and CC prime, and we're requested to find the magnetic field at this point O, which is the center of the arc AC. Now, since I have three sections of different shapes for this wire, I will study each section separately. So for the section A prime A, you can see that I have drawn here the direction of ds, which is the infinitesimal length of the current, in order to solve for the magnetic field using the Biot Savart law. And I have also drawn the unit vector r prime, which is the unit vector joining the infinitesimal current location and the point of interest at which we are trying to study the magnetic field. We can see that ds is actually of the same direction as r for this section A prime A, and this will actually mean that ds cross r is going to be equal to 0 since the two vectors are along the same direction. For the magnitude of B, this is going to be ds sine theta with the theta equal to 0, which will give me sine theta to be equal to 0. And thus B is equal to 0 due to A prime A because ds is along the direction of R. Similarly, along CC prime, we can see that ds is opposite to R, so the angle between them is 180, and sine 180 is also 0. So the magnetic field due to CC prime is also 0. We still need to study the final part of the wire, which is section AC. So along AC, if I actually draw the direction of ds, it's already shown here in the figure. ds follows the direction of the current, which you can see it goes from A prime A, so it will go from A to C, and thus this is the direction of ds. And if I draw R, which is the unit vector joining the infinitesimal current location and the point of interest, R is along this direction. And you can see that the angle between them is actually 90 because R is pointing towards the center, whereas ds is tangent to the arc, and a tangent is always perpendicular to the radius of a circle, and this will result in having ds always perpendicular to the unit vector r. Wherever ds is along this arc, it will always be a tangent, and r will always be along the radius of this arc, because O, which is the point of interest, is at the center of the arc. Thus, we will always have theta to be equal to 90. So if I write down the Biot Savart law, B, which is mu 0 I over 4 pi integral of ds sine theta over r squared, will reduce to mu 0 I over 4 pi integral of ds over r squared with sine theta equal to sine 90, which is equal to 1 for all locations along the arc AC. We can also note something else. To solve this integral, like we said before, we always have to keep everything in terms of one variable. I'm integrating over ds, so it's better for all variables to be in terms of ds, or s actually. However, we can see that r here is actually always constant along the arc AC. Whatever point you take along AC, the distance to the point O will always be equal to the radius, which is A, the radius of the arc that we are considering. So R equals to A at all points of AC, and thus we can take A squared outside the integral. So I substituted r by a, I will have a squared, which is a constant, so I can take it outside the integral, and thus we can actually write the answer to the integral of ds, which is s itself, where s is the length of the arc AC. Now s can be written in terms of what we have as a given in this figure. So s is the length of AC. However, in this problem we are given the radius and the angle theta formed along the whole arc, So I can actually write as in terms of A and theta, the length of any arc in a circle is equal to the radius times the associated angle. So I can write B to be equal to mu 0 I over 4 pi A squared times A times theta. And this gives me mu 0 I over 4 pi times theta. This is the magnetic field at the center of an arc. So this is the expression of the magnetic field at point O. We can, however, consider the obtained result in order to find the magnetic field at a center of a full circle. So the result that we have obtained, which is for the magnetic field at a center of an arc, can be used to find the magnetic field at a center of a full circle, which we call a loop. So to find the magnetic field at the center of this circle, we can simply use the result we have obtained previously, which is mu 0 I over 4 pi A times theta. So this is the magnetic field we have obtained here. And for a full circle, we know that the magnetic field will be due to this expression with theta equal to 2 pi, which leads us to getting mu 0 I over 4 pi A times 2 pi, which is mu 0 I over 2 times A. This is the magnetic field due to a single loop of wire.